Hello students, in the previous video we discussed about the imperfection in solids, that is defects, in which we have discussed about stoichiometric defect. In this video we are going to discuss about non-stoichiometric defects. Let us recall the points which we have discussed in the previous video. We discussed the defects are of two types, that is point defect, line defect. Point defect further classified as stoichiometric, non-stoichiometric and impurity defect. Stoichiometric defect further classified as Schottky and Frankel defect. Let us discuss non-stoichiometric defect in detail. As in the stoichiometric defect, it does not affect the ratio. It does not affect the stoichiometry. But in non-stoichiometric defect, compounds in which the ratio of positive and negative ion present differ from that of ideal chemical formula of such compound is called as non-stoichiometric defect. That means if it disturbs the stoichiometry of the compound, then it is called as non-stoichiometric defect. As shown in this figure, here the ideal in ideal crystal, the ratio between the Fe and O is the same ratio, that is 1:1 ratio. Cation and anion ratio is 1:1. But in this defect, if it is defect is there, the ratio which you can find here, it will not be same. The ratio is actually get differ. So in this defect, the ratio between the cation and anion in the ideal is not equal to the ratio in the case of defected crystal. That's why it is called as non-stoichiometric defect. Let us consider an ideal crystal which have the same number of positive charge ion is equal to the negative charge ion. So when we count the number of positive charge here, so we have total how many A positive are there? Total 8 A positive charge ion and total 8 B negative charge ions are there in this figure. So that means in the ideal case, the number of positively charged ion and the negative charge is equal here. But let one of the ion, that is the positive ion, is missing. Here the positive charged ion is nothing but the metal ion. So if one of the metal ion is missing from their lattice site, at the time it is observed that now the number of A positive is only 7 A positive is there and there is 8 B negative. So it is observed that the number of metal ion get decreased. So in that type of defect is called as metal deficient defect. On the other hand, if in the place of A positive, let B positive is missing. B negative is missing. At the time, when we count the number of positive charge, it will be 8 A positive and 7 B negative. In that case, metal is in excess. So such type of defect is called as metal excess defect. Let us discuss these metal excess defect and metal deficient defect in detail. So the non-stoichiometric defect is further classified as metal excess defect and metal deficient defect. Let us discuss how it will take place. The metal excess defect, that means the number of cation is greater than the anion. It takes place due to the extra cation and due to anionic vacancies. And the metal deficient defect in which cation is lesser than the anion. It takes place due to extra anion or due to cationic vacancy. Let us discuss these 4 points once again in detail. So first we'll be discussing metal excess defect due to anionic vacancies. Here metal is in excess. That means the positive charge, that is cation, is in excess in compared to anion, and it happens due to anionic vacancy. What is anionic vacancy? When the negative charge ions is missing, at that time we can say a vacancy is developed, which is called as anionic vacancies. So let us discuss what is anionic vacancy. This is an ideal crystal which is shown in the figure here. So when any one of the when the ions are missing, let here this one, B negative, is missing. So what we can say, there a hole is developed. So anions are missing, leaving a hole, and in order to maintain the electrical neutrality, an electron get trapped in that hole. You can see an electron is trapped in that hole. So this is called as the anionic vacancy, means a vacancy is developed due to the missing of anion, and in order to make it neutral, electrically neutral, electron take that position. Now when you count the number of A positive ion, that is cation, is greater than the anion. So that is called, it is metal excess. Example for this one, when we heat sodium chloride in the sodium vapor, as we know that sodium chloride is white, colorless white color, but when it is heated in the sodium vapor, it turns to yellow. It means that when an alkyl metal halide heated in the atmosphere of alkali metal vapors, they impart color due to the excitation of electron trapped at the anionic vacancy, which is called as epicenter. It is one of the important question, that why the metal halides, alkyl metal halides in the atmosphere of alkyl metal vapors impart color. So what is the answer for this one? Because of the electron which is trapped in the anionic vacancy, which impart the color due to the excitation of this electron. Let us see further examples for these. In the same way, how the NaCl and Na gives yellow color, similarly, lithium chloride, when it is heated with in the presence of atmosphere of a lithium vapors, it gives pink color, and similarly the KCl with K gives violet color. So that means these all alkali metal halides gives a coloration, and that is due to the excitation of electron which is trapped in the anionic vacancy. The next, we have already discussed the metal excess due to anionic vacancy. The second one is metal excess due to extra cation in the interstitial site. That means the metal ion is excess if one extra cations get entered into the interstitial site. Let us take this example. When ZNO is heated, it observed that it turns to yellow color. So that is due to the metal excess defect due to extra cation occupy in the interstitial site. That means when the ZNO is heated, at the time it turns into zinc ion and oxygen is released and the 2 electron. So in this case, you can find that one extra zinc ion, it takes the position in the interstitial site. Because of this reason, in order to maintain the electrical neutrality, the 2 electrons which is formed, it takes the position of any another interstitial site in order to make the crystal electrically neutral. So here also electrons are there which also undergo excitation, and because of the excitation of electron, it gives a color. So it gives coloration because of the excitation of electron which is trapped in the interstitial site. That is due to the when extra cation get entered into the interstitial site. Let us discuss metal deficient defect due to extra anion. Here metal ion is deficient. That means the number of positive charge ion is lesser in compared to negative charge ions. Metal deficient defect is either due to cationic vacancy or either due to extra anion. In cationic vacancies, the positive ion may be missing from their lattice site. As shown in the figure, it develops cationic vacancy. And the extra negative charge may be balanced by some nearby metal ion, acquiring 2 positive charge instead of 1. Due to this, the 2 positive charge is developed on the another positive ion in order to maintain the neutrality. Such type of a metal deficient defect which is caused due to cationic vacancy is called as metal deficient defect due to cationic vacancy. This type of defect is possible in the metals which show variable oxidation state. For example, ferrous oxide, ferrous sulfide, nickel oxide, etc. Let us discuss metal deficient defect due to extra anion. As shown in the figure, one extra anion is there which occupy the interstitial site, which is shown here. So in the case of extra anion which may occupy the interstitial position, the extra negative charge is balanced by the extra charges, that is the oxidation of equal numbers of cation to higher oxidation state. It takes place on the adjacent metal ions as shown in the figure. This type of defect is called as metal deficient defect due to extra anion. That means one extra anion, it occupies the interstitial site which is shown in the figure, because in order to maintain the electrical neutrality, the neighboring charge metal ion, it increases its oxidation number +1 to +2. Now we can say that it is electrically neutral. So this type of a defect is called as metal deficient. Why it is metal deficient? Because the number of cations are lesser, because when there is an extra anion in this. So in this way we have finished the defects. Let us once again see the classification what we have discussed. That is point defect and line defect. 2 type of defect we have discussed. From this point defect is of 3 types, that is stoichiometry, non-stoichiometry and impurity defect. Stoichiometry defect, it is further classified as Schottky and Frankel. Non-stoichiometry is classified into metal excess defect and metal deficient defect. Again the metal excess is classified into 2 types and metal deficient is also classified in 2 types. So this is all we have discussed about the defects in the solids. So go both the videos, first and second video in the related to the defects, and make a note of this. Thank you everyone.